Hey everyone, this is the video for chapter 6, lesson 1. In today's lesson, we're going to be taking a look at solving multiple linear equations and seeing the relationship of um, more than one linear equations and how they relate to each other. So that's basically the title of our lesson, called Solving Systems by Graphing. So let's just review a little bit of basic terminology here. A system of linear equations is basically two or more linear equations. Solution of a system of linear equations are basically any ordered pairs that make sense, that make all the equations true. So your solutions are any ordered pairs that make all the equations true. So let's take a look at what that means. The first thing we have to do is graph our equations. Now, this type of equation should start to feel very familiar with you. It's in the form of y equals mx plus b. So we can graph this equation as intercepting on 4 with a slope of 2 over 1, so up 2 over 1. And I can go the opposite direction as well. And so my first equation has a line intercepting at 4. It goes all the way through like this. I'm going to use a different color for my second line. This one is intercepting at positive 2 with a slope of 1 over 1, right? Because there's an invisible 1 in front of the x, so the slope is 1 over 1. So I'm going to plot some points here and draw my line. When I'm looking at this visual, there's only one point in which the two lines intersect. It's right here. You can see that very clearly. They cross over at the location of -2, 0. This is what we call a solution of the systems. And so if I were to replace 0 for the x and -2 for the x and 0 for the y, in both equations, I would come out with a true statement. So let's check. For my first equation, I'm going to write this as 0 equals 2 times -2 plus 4. And when I solve it, 0 equals 0. If I plug it into the second equation, it's going to be 0 equals -2 plus 2, which is 0. Okay, so both are true, which means this ordered pair makes both equations true. It is the solution for both of the equations. Let's take a look at the second one here. Now, anytime we don't see an equation as y equals mx plus b, we might need to reorient our equations. So I'm going to bring this down and show my work for reorganizing my equations here. I'm going to add y on both sides, and then I'm going to subtract 2. And now I have x minus 2 equals y, which can also be looked at y equals x minus 2. Okay, this is now in y equals mx plus b form, called slope-intercept form. Then I'm going to use a different color to work out my second equation, which is 3y plus 2x equals 9. So again, I want to get y by itself. I'm going to solve for y. This time I'm going to subtract 2x on both sides. 3y is over here. I'm going to put negative 2x in front because my mx plus b and x is in the front. I'm going to put this as plus 9 because this is a positive 9. Divide by 3 on all sides, I guess, both sides. 3's cancel. I'm left with negative 2 over 3x plus 3. 9 divided by 3 is 3. This is my second linear equation in y equals mx plus b form. Now I'm going to graph. So since I have my blue marker out, I'm going to graph my blue one first. It's at positive 3 intercepting the y-axis, and it's going down to over 3. Down to over 3. I'm going to go the opposite direction. Then I'm going to connect my points. Bear with me because I don't have a straight edge here. It's hard for me to draw these lines on the computer. Then let's graph our pink one. Y equals x minus 2, so an intercept at negative 2. And the slope is up 1 over 1. Continuing that way. You can probably see where my line is intercepting. It's intercepting here at the center. That location, that ordered pair, is at 3, 1. So if I wanted to check, I could replace my order pair y and x and y into each individual equation. So let's do the pink one first. This would be 3 minus 1 equals 2. Does it work out? Yes, 3 minus 1 is 2. Check, that's correct. Let's do the blue equation. So I'm going to write this as 3 times 1 plus 2 times 3 equals 9. 3 times 1 is 3. 2 times 3 is 6. 3 plus 6 is 9. 9 equals 9. Check. That is also correct. So this is a valid solution for the two systems. All right. Let me take this off so I have some room to write down here. Let's review, well, not really a review, but let's go over some of this vocabulary, some new words, and we're going to see this play out in just a sec. So consistent. Consistent, a system of equations that has at least one solution. An independent is a consistent system that has exactly one solution. A dependent, a consistent system that has infinite solutions. And then an inconsistent, a system of equations that has no solution. Okay, so let's break this down and talk about what that means. When we're taking a look at our system of equations, meaning there's more than one equation, so right now what we're focused on is just two equations, meaning I'm going to have two lines. In example A, you notice that both of these equations have the exact same slope. It's -1. So they will have, when I replace the X and Y, I'm actually, because they have to have a common ordered pair, I'm going to realize that I will never get a solution for both of these equations. In other words, if I were to graph them, they're actually never going to cross over. And so if I were to actually graph this, and we talked about this in the past with parallel lines, right? So I've got parallel lines have different y-intercepts. Let's say this is my first line, intercepting at -3. And then I have an intercept at +5, but it has the exact same slope. So with the exact same slope, they're going the same direction, but they're never going to cross because the slope's always going to be the same. So this is what we call a system of equations that have no solutions. And let's talk about what that would look like down here, because we're going to use these three graphs on the bottom to describe them. That would be where I have -3. And then in terms of this first example, example A, it's a -1, so down one, and then to the right one, -1/1. So my line's going this way. And then, so hard to the computer. And then my other line is at +5, but it's going the exact same direction, right? So I'm going to have a parallel line. This is a no solution. When you have parallel lines, there's no solution. How about over here? I'm really not able to tell because the second equation is not written in y = mx + b form. So let's just rearrange it. I think I could divide everything by 3. And then I will have y = 3x - 3. These equations look exactly alike, okay? These are exactly the same line, it's the same equation. And so we're going to describe this as having infinite solutions because every point on the two lines are going to be in common. So if you see a same line, then they have infinite solutions. And so an example of infinite solutions would be where you have a line going this way. I'm not going to try to graph that. And then the second equation would be the exact same line. The exact same line on top of the previous line. Okay. So they would be the exact same line. That would be an infinite amount of solutions. Well, what would be an example of one solution? That would be what we graphed above right here, where they cross at exactly one point. And there's one common ordered pair. So that would be where two lines intersect. And that would be an example of one solution. That's where the lines are probably going to have different slopes and different y-intercepts. Let's describe what this is talking about. So with one solution, the lines intersect in one point. The lines have different slopes. And the equations are consistent and independent. So using the words that we've written above, consistent and independent. Infinite many solutions, the lines are the same. The lines have the same slope and same y-intercept. They're exactly the same equation, exactly the same line. The equations are consistent and dependent. Lines with no solution are parallel. Lines have the same slope, but different y-intercepts. The equations are inconsistent. So I'm utilizing these vocabulary words here to describe the type of relationship that my lines have. All right, we're going to stop here. We'll carry on some more in our next video.